All right, let's continue on with part 2 of our 1.7 on modeling, which is again word problems. So we're going to do one more mixture problem before we switch to distance rate time. This one's slightly different, so if you take a second to read through it, while you're reading through it, I'll just kind of summarize here. So basically the manufacturer has got their product labeled naturally flavored, but it only contains 4% juice. Now there's a regulation that says in order for you to have that labeling, you got to be 20%. So their package is mislabeled. So they got kind of a couple things they can do. They can redo their packaging, which means stopping production for a while of the actual product because they got to do all the packaging, or they can redo existing batches, which they probably have that are not packaged, allow themselves some time to change the mixture and get it up, and then their packaging actually will still be legit. We'll still follow the regulation. So the idea would be, let's take what we've got existing. This one says, identify the amount of pure orange juice the manufacturer will add to 80 gallons of orange soda to conform to the new regulation. So let's just assume we're in the plant. We got these big vats, 80 gallons of orange soda that are not yet packaged. Let's use those up, change the mixture, and then we can, once that's gone, we can permanently change the mixture and keep our packaging unchanged, save ourselves some money. So I imagine myself in the plant doing this. Now it says I'm going to add OJ to get the level up. So basically, imagine you stand over this big 80-gallon thing of orange soda and you got pure orange juice and you're just dumping it in, right? Well, if you dump in pure OJ into the soda, it should bring up the level of OJ, which is the basic idea. So as I start to set it up, X is definitely the amount I'm going to add. That's the question, right? How much should I add? Question defines the variable. And now I'm going to give you guys kind of a little bit of a skeleton outline here. And so again, we want to go concentration times amount all the way through. Now, as you start working with this, again, think of I've got this original mixture. Well, the original mixture is only 4%. So that's 4%. That's that original 80 gallons of soda. It's my job to bring it up to the regulation. Pure. When you add something pure, pure has a concentration of 100%. So if it's pure, it's 100%. That's a 1. And then the idea is get it up to the 20%. Now, the thing about this last piece is that, I added more liquid, right? I had 80 gallons plus more liquid plus OJ. So if I add 80 gallons to start and I added some more liquid to it, then 80 gallons has got to increase by whatever I added. You just kind of, again, reason it out a little bit. So now I've got my equation going. That should be good to go. Also, remember, along the way, every time I did a piece of the problem, I kept doing concentration times amount, all the way through. Always that's the case with mixtures. So here we go, 3.2 plus x equals 0.2x plus 16. Some pretty simple numbers. And do a little dot, dot, dot. I'm not even going to finish the work here, let you guys fill in the blanks, but x equals 16 gallons. So essentially I have to add 16 gallons of OJ to every 80-gallon, let's say, drum of orange soda I have. That'll bring it all up to the concentration it's supposed to be. I can go ahead and package that and not have to change my packaging. Okay, let's switch over to distance rate time. We're going to do this also in pairs. Distance rate time is something that I think is not new to you guys. It's just a concept. You probably talked about it in some science class in middle school, I imagine, or maybe some other science class, and even in high school, or physics possibly. So the relationship, distance equals rate times time. That's what you're used to. We have some other versions here which we will use to help us do some of these problems because we're not always finding distance. Sometimes we're finding time, sometimes we're finding rate. So that's me just solving the original equation for either t or r. But when you're doing these kind of problems, there's really kind of definitely a sort of a pattern to follow. I think if you stick to this, you'll always make this problem easier. So the question is the variable. That's a universal for all word problems. We're going to table these out. It's much easier to organize information in a table. The information that you're going to read, like the actual word problem itself, will not fill in the entire table. It'll fill in some of it. It'll be your job to use what you can fill in to create the rest of the table. And I'll explain that in a minute. Once a table is there, then let's go set up your equation. Set up the equation. There's usually a lot of information in a distance rate time problem, so you really have to weed through like what number in there would actually help me set up an equation, or maybe it's just there's only one equation that even can be done that makes sense. Also, it can be a little confusing sometimes as you're often using like a different part of the table to solve for the original question, and I'll explain that to you guys too in a minute. Okay, so much easier to talk about this if we just go ahead and get started. So a pretty classic problem here, distance rate time. Pilot flew from Montreal to LA, which is distance of 2,500 miles. On the return trip, the average speed was 1.5 times faster than the trip there. The round trip took 9 hours and 10 minutes. what is the speed from Montreal to LA? So right away, the question is the variable. So as soon as I read what is the speed, and I'm going to my table, speed is rate. Now also, distance rate time problems tend to have sort of these parts to them, like the ways to split it up. So there's a there and a back trip. So that, to me, that's kind of the typical split here. So when you read it, that should be kind of clear to you. There's parts as far as organization goes. So what was the speed from Montreal to LA? Well, that's actually the there part of the trip. Question defines the variable, and there's my x. Also, the connection then is I was 1.5 times faster on the way back. And then what else I know is true is that it's the same distance whether I'm going there or back, so 2,500, 2,500. Now, some people are tempted to throw that time in there and go, well, I could do like an x for time, and then I could do 9 hours and 10 minutes minus x. And technically that would be true, but that wasn't the question. So you always got to stick to the variable. The question defines the variable. And then we're also not going to try to jam the 9 hours and 10 minutes into that time, because how do you know the split? There's no way to split that. And again, we're not going to do it algebraically because that creates a variable in a spot we don't want. So we're leaving that alone. We'll come back to that in a minute. What we're going to do is use what we have to define the other part of the table. And so if we're at time, then here we go. Time is distance divided by rate. So we've got 2,500 divided by x, and we've got 2,500 divided by 1.5x. So this is pretty typical. You'll fill in basically 2/3 of the table from what you read, create the other third based on the relationship, and now go search for your equation. Well, here's the thing. The only thing we actually can create an equation out of is time, because you have time there plus time back as an expression, and you have a total time. If you go over the x part of the original x part of it, rate, and rate, well, you don't have another rate, so there's no equation set up. In distance, there's not any variables. So as you kind of weed your way through this, there really should only be one place that creates an actual equation that even makes sense. So we're going to set that up as time there plus time back has got to equal round trip time. Now, something about our time, 9 hours and 10 minutes. Right? You cannot just say 9 hours and 10 minutes, some people would do it, but it'd be not right. 9.1, absolutely not. What you need to do is think about it as a fraction. So 10 minutes is 1/6 of an hour, so that's 9 1/6. And then even better would be to change it to an improper fraction, 55/6. Because for what I'm about to do in terms of the process, this would actually be a much better way to go. So again, think of time as a fraction, fractions of an hour, and then get it switched over. Now, if you're talking about method, this would tie into our solving methods and solving a rational equation. And we know that when you solve a rational equation, the easiest way to get it cleaned up in a hurry is multiply through by the common denominator, which in this case is 6x. So if you start cruising through and doing the multiplication, let's go ahead and knock it out here. We've got 15,000 here, 10,000 here, and 55x, which gets us down to 25,000 is equal to 55x, which is an x of 454.5 miles per hour, which is our answer. So distance rate time, again, there's a lot of organization up front, but that organization pays off, especially in the table format. And then where's your equation? The only equation that makes sense. Okay, let's do one more of those, and we'll wrap it up here for part 2 of the notes. So if you take a second to read through this one, Jack took a trip to Chicago from Minneapolis, about 400 miles, drove a rental car to Madison, met up with a friend to save some money. They decided to ride a bus the rest of the trip. So when I read that to me is the split in the problem. There's some time in the car, there's some time in the bus. So right away I know my table can be divided into those two parts. It talks about the speed, so average speed, Jack was driving his car at 70, the bus has only got about average speed about 50. Total travel time is 7 hours. How long, right? How long? So as soon as you read the word how long, it automatically should take you to the time part of the table. So question defines the variable. Now, the question is about how long did Jack and his friends spend on the bus, so it makes the most sense to me to put X in there. You could put X in car, but that wasn't the question. So I'm going to stick with that. And then what I do know was total time combined in the two, car and bus, was 7. So here's the algebraic split. So if I spent X time on the bus and I spent a total of 7 hours in both, I spent 7 minus X in the car. Now, starting to fill in some other stuff that I know. The car rate, 70, that was clear. 50 for the bus. Distance, I do not know. I know total distance, but you don't know how to split it. And again, you might go, well, why don't I go like x and 400 minus x? Well, that's legitimate, but that's not what the question asked. It didn't ask you how far, it asked you how long. Okay, so stick to the question that defines the variable. That's where the spot I want to go on the table. And then how we'll create the distance one is simple enough. We'll just use rate times time as distance and create the second part of the table. So here we're going to have 490 minus 7x, and here we've got 50x. Now, what is the actual equation? Well, rate and rate. No variables, no like combined rates. That one's out of the picture. Time and time, well, you could say 7 minus x plus x is 7, but all you would do is prove that 7 equals 7. That would get you nowhere. Distance, I have two expressions, and I got a total distance. So there we go. Distance in the car plus distance in the bus equals total distance. If I put those two together, which means I'm just going to add these two and set equal to 400, I get negative 20x plus 490 is equal to 400. And then a little bit of quick algebra solving, and we got it. 4.5 hours on the bus. So one thing I would just say quickly before we wrap this one up is that it may seem a little weird because the question was how long, and you used the distance part of the problem to figure it out, but that's okay. Your variable is defined as time. The fact that it's used somewhere else doesn't change the fact that we're still solving for time. Okay, and that's going to be the end of the Part 2 1.7 video notes.